Okay. First of all, thank you for giving me the opportunity to present my work here. My name is Yuan Yuan. My thesis is entitled Models and Algorithms for the Last Mile Delivery with Multiple Shipping Options. I was supervised by Professor Simé, Professor Gatrouza, and Professor Augier from Saint-Etienne. This is the outline of my presentation today. First, I will introduce the context of the studied problem and give a formal problem description. Then I will divide the interested problem into two cases and will briefly introduce the algorithms developed for these two problems. Then I will conclude my thesis work. First, about the motivation. Nowadays, due to the wide use of internet and its convenience, e-commerce is becoming more and more popular. The global e-commerce sales are estimated to reach 4 trillion this year. This increasing e-commerce poses a huge challenge for the last mile delivery, since the items ordered online need to be delivered to customers. Currently, there exist several delivery options in the last mile delivery. The most common one is home delivery. And packages can also be delivered to pickup points, such as lockers and stores. For example, there is a company called Pickup. They have 44,000 pickup points in Europe. In recent years, there's a new concept called trunk or in-car delivery. Customers choose their car as a delivery location. Nowadays, Amazon are providing this in-car delivery service to its prime customers in more than 50 cities in the US. All these delivery options can be combined and proposed to customers. So when customers purchase online, instead of choosing only one delivery location, customer can indicate a set of delivery locations with the corresponding time periods. Then for the planners, they only need to choose one of the locations provided by the customer to make the delivery. Here I will give you a small example. The triangle represents the depot. All the locations associated with a single customer are grouped into a dotted circle. For this customer, for example, he will stay at home during 8 and 10 o'clock. Then he will drive his car to visit a friend during 11 and 14. He will then drive his car to go to a shopping mall during 15 and 17. And on his way to the shopping mall, he will pass by a locker. We may have several customers indicating their delivery locations, and suppose there are 2 vehicles available for the delivery. A feasible solution could be like this. That is, each customer is visited at one of its locations respecting the corresponding time window. We are inspired by this application, but we are not restricted to it. Now I will give you a formal problem description. Given a direct graph G, a vertex set V is partitioned into K+1 clusters. These clusters are exhaustive and exclusive. There is one cluster representing the depot. Each vertex is associated with a time window. Each cluster is associated with a demand. The arc set A is only defined between different clusters. There is no intra-classed arc. Each arc is associated with a traveling cost and a traveling time. There is a fleet of M homogeneous vehicles with capacity Q locating at the depot. The objective of this problem is to find at most M routes such that the total traveling cost is minimized, each cluster is visited exactly once, time and capacity constraints are respected. We can divide this problem into 2 cases. When M equals 1 vehicle available for the delivery, it is the generalized traveling salesman problem with time windows, GT-SPTW. When M bigger than 1, it is the generalized vehicle routing problem with time windows. Actually, the GT-SPTW and GVRPTW, they belong to a big category of non-Hamiltonian vehicle routing problems, in which the visit of all vertices is not mandatory. In the thesis, we did a survey on this problem. Here, I only present the most relevant ones. We do not consider time window. These two problems reduce to GTSP and GVRP respectively. When each cluster contains only one vertex, these two problems reduce to TSPTW and VRPTW respectively. For the GVRPTW, when the time windows for the locations in the same cluster do not overlap, it reduces to a VRP with roaming delivery locations. And actually, in this problem, only the trunk delivery we discussed before is considered. Now I will briefly introduce the branch and cut algorithm for the GTSPTW. We follow the standard branch and cut scheme. The initial model is based on the MIP formulation. In this thesis, we proposed 4 MIP formulations for the GTSPTW, and we compared them theoretically. The best ones are used for the branch and cut algorithm. Then we develop a heuristic to obtain an upper bound and use it as a warm start for the branch and cut. Inside the branch and bound tree, each time a fractional solution is obtained, separation algorithms are used to detect violated inequalities, and the violated ones are added to the model. The algorithm ends when the optimal solution is obtained or the time limit is reached. In the thesis, we propose 5 families of valid inequalities for the GTSPTW, and due to the time limitation, here we focus on 2 of them. First, arc or vertex inequalities. Due to time window constraints, a vertex and an arc may not be simultaneously present in a feasible solution. For example, here, for vertex H, there is no feasible solution going from H to vertex J passing through arc ij, and there is no feasible path going from vertex I to vertex H passing through arc ij. And in one cluster, there may be several vertices at H that couldn't be simultaneously chosen with arc ij. So in this case, only one of these vertices and arc ij can be chosen in the solution. Second, sequential ordering inequalities. They are based on the precedence between vertices. For example, here we have a timeline and 2 vertices J and I. J and I have to be visited between 8 and 10, 12 and 14 respectively. It is obvious that J has to be visited before I, so we say J precedes I. For all the vertices that have to be visited before I, the predecessor set of I. Based on this concept, we have the pi inequalities. Suppose this denotes the vertex set. 0 represents the dipole. We have a set S, including vertex I. The rest of the vertex set is called S bar. S bar includes the dipole. If I is visited, then there will be an arc going from S to S bar. But we know that all the vertices in the predecessor pi I has to be visited before I. So we can exclude these vertices from S the group part. This gives us the pi inequalities. Due to the presence of cluster, if I is visited, then the other vertices in the same cluster with I cannot be visited. We can further exclude these vertices from the blue part and the gray part. Now I will introduce you some computational results. The instances are generated from the benchmark of the GTSP instances by adding time windows. K and V represent the number of clusters and vertices in these instances. Here we compare the results of using simplex with and without the proposed valid inequalities. First, compared with the results of linear relaxation, the average lower bound obtained at the root node is improved by 13.5% when only the simplex automatic cards are added, and 55% when our user cards are added. Within 1 hour of computational time, the largest instances that Cplets can solve has 12 clusters, while our branch and cut can solve instance with 30 clusters. Moreover, our branch and cut can systematically solve instances up to 24 clusters and 120 vertices to optimality in less than 3 minutes. Next, I will introduce the column generation-based heuristic for the GTS-PETW. This algorithm is based on a set covering model that relies on an exponential number of variables representing all the feasible routes. However, generating all the feasible routes is not tractable. Therefore, we maintain only a subset of feasible routes, iteratively populated along the algorithm. The algorithm has 2 phases. Phase 1 aims to construct some feasible routes, and phase 2 explores the dual information of the linear relaxation of the set covering model to generate additional routes with negative reduced costs. There are some shared parts, for example here, local search in both phases. In the following, I will introduce the key ideas of the main components in the algorithm. First, the construction heuristic. Actually, it is a parallel insertion heuristic. Inside of it, we embed a route optimization procedure. Why we use this procedure in the construction heuristic? Actually, it optimizes the visiting of a set of clusters. Here we give an illustration. Suppose we have a partial route visiting cluster 1, 2, 3 at vertices 2, 4, 7 in green color. If you want to insert cluster 4 into this route, with classical insertion, there will be 4 possible insertion positions, 1, 2, 3, 4. But with the route optimization procedure, we can have a better route like this. We notice that here, the visiting sequence of cluster changes from 1, 2, 3 to 2, 1, 3. And the visiting vertices could be changed too, from green vertices to red ones. In general, the route optimization procedure increases the possibility of finding more feasible solutions and also finding solutions with lower costs. After the construction heuristic, the set covering model is solved in the hope of finding better combination of the routes generated so far. Then the solution obtained is further improved by the local search moves. The key idea of the local search moves is to allow the change of the predecessor and successor vertices. Here we take the insertion operator as an example. Suppose we have a partial route visiting cluster CH and CK. If we want to insert the cluster CU, if we use the classical insertion, the route will be in the dotted line. But if we allow to change the predecessor vertices and the successor vertices, we can have a route with a lower cost in the solid line. For the local search, we apply 2 types of moves, inter-route relocation and swaps. Further, finally, the column generation part. The particularity of our column generation is that we identify the routes with a 0 reduced cost in all the routes that we generated so far, and then we apply local search moves on these routes with 0 reduced cost to generate more columns. Now I will show you some computational results. First, we test our algorithm on the benchmarks of VRP with mean delivery locations, VRP RDL. VRP RDL plus home means that each customer has a home location with a time window equal to the whole time horizon. Using the proposed algorithm, we can always obtain the optimal values provided in the literature or improve the best knowns for instances with up to 120 clusters within 5 minutes. Then we modify these instances taking into account the pickup points. Results show that the cheapest solution is obtained when all the delivery options are available. Computational results on two other sets of instances also show the efficiency and the competitiveness of the proposed algorithm. Finally, I conclude my thesis work. We studied the routing problems arising from the last mile delivery with multiple shipping options. Models and algorithms are proposed for the underlying problem, the GTS-PTW and the GVR-PTW. A paper is published in 4OR based on the 4 MIP formulations for the GTS-PTW, and a paper is published in Operation Research Letters based on the supervalid Miller-Tucker-Zemelin constraints for routing problems with time windows. The branch and cut algorithm for the GTS-PTW leads to a paper in IJOR, and the column generation-based heuristic for the GVR-PTW is now under the 3rd round review of the Transportation Research Article. Here, I conclude my scientific productions and collaborations in the following. That's all for my presentation today. Thank you very much for your attention.
Thank you, Yuan, for your presentation, especially knowing that you have the time difference and it's not easy to manage that. So now 2 people are going to ask you some questions, so Jacob Kuschinger and François Cloutiot. So Jacob, you have the voice. Okay, if Jacob is not ready, then François.
Yep. Can you hear me?
Yes, I was talking. Yeah. I was talking. I'm sorry.
Okay.
I forget to turn on my microphone.
Okay, so Jacob, please.
I'm very sorry about that. So I said thank you very much for your interesting presentation, Yuan, and I enjoyed it a lot. And what I find very interesting that on the one hand you present exact results, you present different formulation with valid inequalities and for the generalized TSP, and on the other hand you present a column generation based heuristic for the generalized VRP. But I wonder what are your learnings that you take from all the exact part, so from your from the valid inequalities and from the formulation, and you put them to the generalized VRP. So what parts of all these, I would say, exact mathematical part could you reuse for the GVRP? So what would this mean, for example, when you would think of a branch and cut and price approach where you combine some valid inequalities within a branch and price or something like this? Or maybe you have other learnings?
You mean what we created for the branch and cut, what we can use later for the GVR-PTW, right?
Exactly. What would be your perspective on what kind of things from your valid inequalities and the different formulations you did also for the TSP, you can take them over to the VRP?
Yes, it's like now our columns are generated heuristically, but when we if we want to maybe at last phase of the column generation, we can use the it's like we can use the exact method to generate optimal route for a set of clusters.
Okay.
But this will takes time to do it.
Of course.
It's not very efficient, but it is efficient for routes maybe around 15 clusters. But if it's longer, then it's not that efficient.
But for example, the valid inequalities you find for the GTSP, could you use some of them for the VRP part?
For the VRP part?
So some of these infeasible, you showed us that some feasible, some node combinations are infeasible, for example. Could this be used in the VRP part? VRP?
I mean the valid inequalities, right?
Yes.
For the column generation, for the algorithm we develop now, we don't use any valid inequalities there for the column generation heuristic now.
Yeah, that I understood, but the question would be, could you project yourself into using some parts of it? Is something possible, you think?
I think it's possible. I remember, how to say, the GVRPTW when the time windows.
Okay, then.
Sorry. I need to think about this problem. I remember when doing the GVRPTW. Actually, I use the GTS-PTW, the exact method, in some parts of the GVRP, but I couldn't remember now. I'm sorry.
Okay. It doesn't matter. I give the word to, it's François, I think.
Okay, thank you, Jacob, and François, please.
Okay, can you hear me?
Yes.
Okay, thank you. So, yeah, I had a question, but maybe you answered it in your presentation, but I will ask it anyway. When you work on TSP without time windows, the best model by far is the one based on subtour inequalities. I wondered if it was possible to have a model based on subtour inequalities on some other inequalities for the time windows instead of relying on this weak MTZ model. What is your opinion?
I'm sorry, I didn't hear it clearly because the connection cuts a little bit. You said when I don't consider the time window.
So my question is, yes. Do you think you can come up with a model that does not rely on MTZ-based inequalities?
We have because the MTZ is a polynomial. They have polynomial number of constraints. But in the model, in the branch line cut, actually we also have the generalized subtour elimination constraints to cut the subtours.
Yeah, but can you get rid of the MTZ variables in a model?
Yes, I can. If I have the generalized vehicle, if I have the generalized subtour elimination constraints, I can delete the supervalid MTZ constraints, but it's just because with it, it can improve my linear relaxation. It can help my bond, obtain a better lower bounds. So I added.
Okay, but subtour elimination constraints do not handle time windows. Am I right? So you need some inequalities to make sure that the time window constraints are satisfied.
Yes. Yes, it's like we should, but it's like for a problem with time windows, for sure we will have constraints to make sure the consistent visiting between two vertices, and any of these kind of constraints will eliminate the subtours, because the time has the time itself can present this kind of subtours.
Okay.
Okay,
and Marc, do I have time for another question?
Yes, of course.
Okay, thank you. So I had another question about chapter 4 in your heuristics.
Yes.
As far as I understood, it's kind of a two-stage heuristic. First, you decide in which order the clusters are visited, and then you choose which vertex is used for each cluster. Am I right?
You mean in the construction heuristic?
Yep, in the construction heuristic, yeah.
No, actually, it's not. I decided the sequence first and then the vertices later. I did it together with the route optimization procedure.
Okay, but the route optimization procedure takes a sequence of cluster as an input. No?
No, it doesn't take the sequence of cluster as an input. It optimizes the visiting for a set of clusters. It takes the set of clusters as an input, not the sequence of the cluster.
Okay, sorry, maybe I misunderstood. Okay, so in your local search operator, okay, so maybe I misunderstood. So I believed you were working on the cluster order, and then you had some exact method to find the best vertices to visit. Is that not the case? Okay. So maybe my question was not relevant. Okay, thank you for your answers.
Thank you.